Hi guys, and welcome back to week 2 of series 1 of the Rocket Propulsion Masterclass, where the guy who made this is going to be teaching us all about this. Rocket Propulsion Elements by George P. Sutton. This week we're going to be jumping in right where we left off and talking about entropy. So, let's jump right in.
So, in section 3.3, he uses this word isentropic. Now, there's a piece of thermodynamics which makes even physicists go pale when they think about it. That's something called entropy. And a great many people have only got a loose idea of what entropy actually is.
Isn't it basically the amount of disorder in a system, or the amount of energy in a system, and although the energy can't be created or destroyed, it naturally wants to get more spread out and evenly distributed?
That's absolutely correct, but and as a physics explanation, that's very good. As some engineers wanting to actually use this, if we've got some substance and we put some heat into it, a little tiny bit of heat, and its temperature is 100 Kelvin, whatever, then the change of entropy that occurs is that little tiny bit of heat that we put in joules, divided by the temperature that we put it in at as Kelvin.
Now, heat in joules?
Yes.
So, I mean, joules is a measurement of energy, so you're referring to the amount of energy that the atoms have.
So it's the heat is energy.
Right.
It's the, as you quite rightly said, it's the heat, the energy tied up in the motion, the disordered motion of the molecules within the gas.
Right.
So each molecule's got kinetic energy. They're all travelling in different directions. We lump all that together, and then we call that heat.
Okay.
Many centuries ago, it used to be believed that the heat was something physical that travelled between a hot body and a cold body. That the heat in the early days was called caloric, and so an amount of heat transferred. We now know that what happens if you've got a hot block of copper and a cold block of copper, you put them together, the high energy hot molecules crash into the cold molecules, they move about faster than they did before.
Okay.
And so
the hot block loses a bit of kinetic energy in the process, and so they even out over time.
They even out. So what's quite important about this, and where the whole usefulness of entropy comes from, is that if you put a cold block next to a hot block, the hot block cools, the cold block gets hotter, and eventually they finish up at the same temperature. If you put ice into a glass of water, ice melts and eventually becomes the same temperature as the rest of the water. Now, nobody in the entire history of physics that we've recorded has ever seen a glass of water suddenly rise in temperature and spit out a cube of ice. And that's where the entropy concept comes in.
Okay.
The entropy of the universe only ever increases. So if you've...
although it can decrease in localised areas, but it must be balanced out by increases
perfectly,
in the greater amount.
Absolutely. So a lot of people, for example, look at, hang on, I've got an egg, and it turns into a hen. The hen is obviously a very ordered structure, whereas the egg is actually quite disordered.
Right.
Now, people have actually done thermodynamic measurements of that, and sure enough, even though the entropy of the hen is lower than the original entropy of the system, the entropy of the universe actually goes up in the process, and the egg gives out heat to the rest of the universe in the process of turning into a hen.
Right.
So we can't beat this. It's very, very fundamental, and something that used to annoy me immensely when I was a lot younger, because you can't help feeling, and everybody should feel, this can't be right, we must be able to defeat it. Really want to learn about thermodynamics, try to defeat the second law, which is the bit that talks all about entropy.
Right.
Now, an isentropic system is a system where the entropy does not change. And that can only happen in a system which has got no friction, no viscosity, etc., anything that can dissipate heat into some lower form.
Which realistically can't happen, but I presume we're looking at a perfect scenario here.
Exactly.
We'll get a certain percentage.
So you're absolutely correct. In any real situation, that has to happen. But what we are doing here is making some idealizations on the fact that the changes of the increases in entropy are going to be very small.
Right.
Now there's a couple but different. We use a term called adiabatic. Now that's just a fancy way of saying constant temperature. So in a constant heat energy, sorry, not constant temperature, constant heat energy. So in an adiabatic system, no heat crosses the wall into the system. So all the heat's contained within the system and it's isentropic. Okay. So that anything that changes place inside the system, which we're going to cover in chapter 3.3 here, any changes that take place inside of that, we can now sort of address. So what we've got then is constant energy,
right,
constant entropy, and what that actually implies in terms of the equations comes out in the chapter. But then also in a rocket nozzle, there's another important principle, constant mass flow.
Right.
So that any section in the nozzle, the amount of mass passing through any of those sections in any unit of time is the same.
Okay.
So we've got that. And then we're going to throw in where we started with the perfect gas law. And so what George Sutton does then is roll all that lot together in section 3.3 here, put some equations together, and lo and behold, what we find that we can calculate is the velocity of the gas in terms of the pressure ratio in the nozzle for a given starting temperature and molecular weight.
Okay.
And we come down to equation 316 here, in which that is a nice little equation, got a square root sign in it, but
okay.
all right, all our calculators have got a square root function. Okay, so we've got to a point then where if we know the pressure ratio of a nozzle, we can now calculate what the velocity of the flow is at that point.
Right.
That's all very interesting, but a lot of the time what we've got is a nozzle in which we know what the area of the nozzle is divided by the area of the throat. And so what we want to do is to relate the actual conditions in the nozzle to the area ratio. And so the next step is to put together some equations which make use of the continuity, as we call it. So we know that the mass flow is constant, but what we've got is a perfect gas at a volume, a temperature, and a pressure. Now, for a perfect gas, if you know the pressure and temperature,
right,
you know what the volume of a kilogram is.
Okay.
If we know how many kilograms a second we've got, then we know what the flow rate is in cubic meters through the volume relationship.
Okay.
And then if we know what the velocity is, because we've already got the pressure relation that tells us the velocity,
right, then
continuity says that the mass flow is equal to the density times the velocity times the area.
Interesting.
And then after that, then we can calculate the area ratio. And so by the time we get to equation 319, 320, and on through 324, we've got a set of relationships which will tell us how the pressure, the mass flow, and the velocity, the area ratio, and the velocity are actually varying down this nozzle. So there's one slight thing that should be warned of here. This all assumes that the gas is travelling in one direction. It's a one-dimensional analysis. Now, any real nozzle has actually got diverging sides.
Right.
So some of the gas is actually moving at an angle. But we come back
because
and
it hits the wall and then it bounces off at an angle, or
oh
it's
yeah,
just,
if you've got a conical nozzle and the flow is just going down it, then obviously the flow that's next to the wall is going off at an angle.
The wall. So presumably in a perfect rocket nozzle, it would be bell shaped, but it would sort of straighten out.
Correct. So modern rocket nozzles, I say modern, they've now been around since the 1950s, are as you say, a bell-shaped contour, and the object is to try to turn the flow axially. Now, just as an aside, there are actual exact solutions to that problem, but the nozzles that you get are humongously long if you try to do that. So in a practical rocket nozzle, we squash it up somewhat, as a result of squashing it up, we actually get something called shock waves generated inside the nozzle. Now, I mentioned that a point on the nozzle will lead to something called a Mach line, which leads out into the flow. And the pressure change across a Mach line is very, very tiny, so infinitesimally tiny, it makes no difference. But in a shock wave, we get a finite jump across a shock wave, and that generates entropy.
Okay.
So when we have a real practical rocket nozzle, a bell-shaped nozzle, which is turning the flow more quickly than the flow actually wants to turn at, the consequence of that is it generates entropy. But provided that you don't go overboard with it, provided you turn it slow enough, the amount of entropy being generated is actually quite small, so you can ignore it to a first order.
So less than a percentage of efficiency losses.
So we'll come on to nozzle efficiencies, I think, towards the end of this chapter.
Okay.
So what we've covered then in this so far is that we've got a combustion chamber where we're generating hot gas. We won't worry about the combustion mechanism at the moment. That gas has a molecular weight, it's got a specific heat and a combustion temperature, it's got a pressure, and we're now going to let the pressure fall as we go down the nozzle. And what happens first of all is that we find that the velocity is increasing faster than the volume, and therefore to pass the correct mass flow, then the nozzle contracts. And as if by magic, we finish up at the throat, that the flow is exactly the speed of sound at the throat. Mach number equals 1 at the throat. So within this converging region, what's going on in there is determined by the shape of the contour. Downstream of that, the flow becomes supersonic, and what happens now is that the volume is increasing faster than the velocity, and so downstream of the throat, the cross-sectional area is increasing more rapidly in order to pass the mass flow. And so we finish up with a nozzle which contracts to the throat, speed of sound at the throat, and then it goes supersonic in the nozzle exit area. And the equations to calculate all that are given here.
Okay, so we think that's a good place to pause. We're going to stop here and pick it up the exact same place next week. In the meantime, make sure you write all of your questions down in the comment section, and we'll see if we can get around to answering them in future installments. See you next time.